And here's the one circle. All right, so what does it say?
A matching network using a reactive element in series with a length d of t line
Right.
is to be used to match with a 35 minus J50 load.
All right, so yeah, all right, so we have ZL here. And ZL is 35 minus J50, right?
Yes.
And what's the impedance of the transmission line?
100 ohms, and we're at 1 gigahertz.
F equals 1 gigahertz.
Find the
Distance from the load, right? And find the element, right?
yeah.
Does it limit the element to be a capacitor or inductor?
It does one with a series capacitor, one with a series conductor.
All right,
Find
we're
the
going to
value
do
of
both. I'm going to show you how to do this problem. It's a logical, this is one of those things, if you know what you're doing, it'll make perfect sense, and it should be almost obvious if you try it. So first of all, we're going to go ahead and with the Smith chart, we're going to get the normalized input impedance. I have a bunch of markers here. I didn't walk off. So first, normalized input impedance is going to be really capital ZL over Z naught, and that's equal to 35 minus J50 over 100, right?
Yeah.
So that's going to be, let's see,
0.35 plus minus J 0.5.
0.35 minus J 0.5, and that's going to be, just thinking, so 0.35 is a circle. If you look at this, if this is R equals 1, 0.35 is about that big. Take a look and see if you can find it. And then we have minus J 0.5, so that's about here is that trajectory. So about here would be ZL. Take a look in your Smith charts, and that would be 0.35 minus J 0.5. Can you all find that? Label at 0.1. With me, class? Mm-hmm. Right now, next, take your compass. Hope you guys got good compasses. Uh-oh. Is that one of those? Yeah, those things tend to mess up, but he's got a good one right there. You take a good compass, go ahead and move it from the center to this point right here. This is your magnitude of gamma L, and just put a circle of that radius. Something like this. Can you all follow me? Just do it. So just a circle, 1 point here, 1 point here, and draw a circle. That's a constant reflection coefficient magnitude circle. Do you all see that? Okay, I see people do it. Those cheap compasses tend to just open up on you if you're not really careful. He's got a good one. You do have a compass, don't you, sir?
Oh, yeah, I already drew one, yeah.
All right, that's fine. We'll make sure everybody does. And do you have one, Chase?
Yes, sir.
Okay. You're going to need it for today, for your quiz. All right, so now here's the thing. Come out here and draw a line straight through that point, and you're going to see something wavelengths towards generator. I call it a mile marker, but tell me what that is. Because we're at the road.
Oh, it's a 0.4196.
Confirm that, people. 0.4196. It looks about right, lambda. So it's that many fractions of a wavelength. Everybody got that?
Yeah, I get about that.
Now, when we move from the load towards the generator, we're moving in this direction. You all follow me?
Mm-hmm.
Now look right here. If we stop at this point, just listen before you do anything. If we stop at this point, our normalized impedance will be 1 plus JX. You all follow me? We don't know, y'all, because we're at the one circle. That's my idea, right? If you keep going, you're going to come to this point. This point is 1 minus JX. Y'all follow me now? Yes, sir.
So it's just in terms of like, not necessarily just this problem, but it's whatever that JX we're looking for.
We
It's
don't
gonna be
know what that is.
Or like, it's whatever is intersecting.
With one circle. All right, it's intersecting this circle you're drawing, intersects the one circle here.
Right.
So if you're hit the one circle, you got 1 is the magnitude of the real, The imaginary is to be determined. You all with me on this, class? Now, here's the rationale behind this. Let's say we go from here to this point. Just watch. Draw a line right from here to this point, and tell me what this wavelengths towards generator is here. And then draw a line from here right through this point. And I want the wavelengths towards generator here too. You'll see why. Take a careful look. Make sure you can read your Smith charts. Because if you, I mean, there's very little, there are no partial credit points on these kind of things. You got it, it's either right or it's wrong. There's nothing, you got to know this stuff. You all with me? So what's this one?
That one is, you going towards generator, right?
Yeah, you have to go, if you're at the load, you can only go towards the generator.
It's got to be 0.1738 maybe.
0.1738 maybe. I give you it. Now what's this one?
0.326.
0.236.
I'm sorry, 326.
326. 326. Has to be greater than 0.25 because this is 0.25 right here. Everybody? Now, hear me on this one. Now look. Think about this. We're at 1 plus Jx. That's normalized. If we take it out of normalization, it would be Z naught, right? Plus J Z naught times X, right? Now, here's the beautiful thing. If we can get rid of that Jx Z naught, it's matched, isn't it? If you go into Z naught, there's nothing reflected. You all follow me on this? That's the idea. So what do? If we stop here, right? Then for the normalized impedance, I want a value that would be, if this is plus Jx, I want minus Jx here. By the way, tell me what this value is here where we intersect. Because this is going to be 1 plus J something. Can you tell me what that is?
1.4.
1.4? Take a look at it.
Yeah.
All right, 1.4. And what's this one?
Minus 1.4.
Exactly. It's going to be 1 minus J 1.4. Now, if we stop here, right? Just listen to me, right here. We would like to add a minus J 1.4. So here's the deal. If we start, here's our load. This is going to be the first one. Here's ZL. This is Z naught. We're going to go a distance, and I call this D1. And we're going to stop right here. So how far do we go? We started here, we're going to end there. So we're going to end at 0.1738, right? That's the mile marker we stopped at. We subtract this from it, 0.419.
Looks like a 6.
Something like that. And you'll notice it's negative. So we have to add half a wavelength. And this is how many wavelengths we're going to move. This is going to be the, I'll call it D1. What is that?
0.2542.
0.2542 lambda. So over here, that's how far we move. 0.2542. And when we hit this point, we have to add a minus Jx normalized impedance. But that means that the actual impedance would be minus Jx times Z naught because it's non-normalized. Can everybody follow the rationale behind that, right? And when we add that together, this will cancel the reactive component and you'll just have Z naught. That's the way matching works. You want just the thing to look like Z naught. You come from Z naught, you go into Z naught, there's no reflections. That's the idea. Can everybody follow me on that? All right, so what's that value going to be? Well, I have minus Jx Z naught. What element has a minus J impedance? A capacitor, doesn't it?
Yeah.
Capacitor is minus J omega C, right? So that means minus J omega C has to be equal to this. All right, that means get rid of the minus J, and I have X times Z naught is equal to omega C, right? Or I'm sorry, 1 over, jeez. It's minus J over omega C. I'm so sorry about that. capacitor is 1 over J omega C is the impedance. My bad. Okay, y'all follow me on that? Capacitive reactance is minus J over omega C, correct, class? So minus J over omega C has to be this. The minus J's cancel. I have x z naught is equal to 1 over omega C, and therefore C is equal to 1 over omega x z naught. Now that's for this problem, but you'll notice I have to account for the normalization. All right, because when we hit this point, the normalized value is 1 plus jx. We have to denormalize that. We want to add a normalized value of minus jx, and that means to take it out and bring it into the unnormalized world, we have to multiply that by z naught. Correct, class? All right, so what's this value going to be? Well, it's 1 over omega is 2 pi f. You said f was 1 gig, is that right?
Yeah.
All right, so it's times 10 to the 9th here. And then it's times x, and you said x was 1.4, is that right?
Yeah.
All right, it's times 1.4, and then it's times z naught, and you said z naught is 100. So this should be the value of C. Can you give that to me?
1.14.
For C?
1.14 pico.
Oh, okay.
Yeah, sorry.
That makes sense. 1.14 picofarads, 10 to the minus 12, right? Just everybody follow on the reasoning behind this. To get a matched impedance, it means you have to look into Z naught, and you have to get rid of the reactive component. That means you have to travel from this point all the way until you intercept the one circle, and then you have to get rid of the impedance component, the J, or the reactive component. With me, class? That's the first part. I'll call this design A. It's using the capacitor. Now, if we want to use an inductor,
Camera.
thank you. Just put it over. I wish it was wide angle and I wouldn't have.
Yeah, I gotta keep moving
The
it.
guy that does it in the morning, his name is Michael Smith, and he has a really easy adjustable stand, but that will work too. I know it works because I've had students use it. Now, follow me on this one. If we're going to move to, this is part B. All right, B design. Now, here's my ZL and my Z naught. But now I have to move, I'll call this D2, and here's how far. I started here, I have to move all the way around to here. Y'all with me? Everybody follow me on that? And the reason is I know this is going to be 1 minus J. So the real part, the normalized real part is 1. That's where we have to be to do impedance matching with series elements. Y'all with me, class? Take a moment, make sure you see this. Okay, let's go. So I'm going to move how far? I ended up at 0.326, right? This is going to be D2. I ended up at 0.326. That's the mile marker I ended on. I have to subtract this from it. 0.4198, right? And that's negative. Do you agree with that? So I have to add a half wave because it's negative. So then I add 0.5 to it. And what do you get? And this will be in terms of wavelength.
0.4064.
0.4064 lambda. Agree? Because it is in terms of wavelength. Agree, class? By the way, you'll notice these matching networks only work at one frequency, technically. I mean, there is a bandwidth. There is some region of frequency, but because the wavelength is a function of frequency, these only work at really technically one frequency. They have a small little bandwidth they work over. There's tricks where you can make it work over all frequencies, but this is not it. But this is the most commonly used matching network there is. So I move a total of 0.4064 lambda. Now, I'm here. I have 1 minus J 1.4. I got to get rid of it, right? I got to get rid of that minus J 1.4. So here, the normalized value I add is going to be plus J 1.4. And again, I'm showing you a normalized value I add there. With me? Okay, what impedance? I'm going to erase this. What element has a plus J value?
Inductor.
An inductor, right? So the impedance of an inductor is J omega L, right? Now, if we normalize it, we could set it equal to that. So to normalize this, I would divide that by Z naught. I'm just showing you the different ways to do this. So that would be the normalized impedance of the inductor. Do y'all agree with this, class? Now I have to set it equal to J 1.4. You can see the J's cancel, correct? And now what do you get? L is equal to 1.4 times Z naught, right? And it's divided by omega. So for ours, it's 1.4 times 100 divided by 2 pi times 10 to the 9th. Give me that answer if you don't mind. That's inductance.
I got 22.3 nanohenries.
Is that right, class? Nanohenries. All right, those are the two possible ways to do it with a series element. You're going to see shortly we can do it with a shunt element or a parallel element too, but we'll be working in the admittance domain. Does this make sense to you, everybody? Impedance matching is used all the time, and it's used everywhere. All the time and everywhere. So next, after that, you got another problem for me, don't you? Surely you do. All right, now I'm going to erase this. Because we're going to get into impedance matching using shunt elements. And that's kind of neat. Parallel. This means shunt is parallel. And we do that in the admittance domain, not the impedance domain.
So fun.
And Dr. Wintler's book has a lot of examples.
These are two. Yeah.
I don't care about the answer. Sweet. Alright. So we need these two. That makes sense.
All right, get another Smith chart. A fresh one. Hopefully you guys printed off a bunch. I gave you a ton of them.
I got the whole thing right here. If you want
He
one.
came up to
My
my office.
office, I just gave him. I got like, there's a bunch in there.
They're not the big ones, though. I like the bigger ones, the really big Smith charts, like the one I emailed you guys. That's smaller. I mean, isn't that smaller? Or maybe it's full size.
This is,
Big enough. I mean,
All right.
yeah.
Some, if they say black magic, they're a little small. I guess that's okay. I like it bigger, though. All right. You guys need some? You need a Smith chart? You got some? Good. Got to have a good compass and a straight edge, too. All right. Now, what's the next problem?
It's 236. I
Okay.
can read it out. says-
Yeah, go ahead.
A matching network consists of a length of T-line in series with a capacitor.
All right,
Determine
hold on. Yeah. So now we got load. Let me just draw this because, so we got load, capacitor, go ahead.
Determine the length and wavelengths required of the T-line section and the capacitor value needed. So it's at 1 gigahertz for the frequency, and you need to match 10 minus J35 ohms load,
And what's the Z0?
50 ohms.
50 ohms. So we have to find the distance D and the capacity. Remember, he gave us a capacity. I want to give you a tip too. Almost always, not guarantee you, almost always when you talk about putting something in series, because oftentimes we have DC biasing requirements. What's the impedance of an inductor at DC, anybody? Technically. It's like J omega L. What is omega for DC? Come on. 2 pi times 0 is 0. It's 0, right? 0 times L is 0. The impedance of an inductor at 0 at DC, it's a short circuit. It's a piece of wire. You all follow me, class? So they usually want inductors in series and capacitors in parallel. And the reason is DC biasing can be used if circuits are designed that way. You all hear me? Because did you all have your analog electronics? Okay, then you don't know what I'm talking about. with analog electronics, you'll find for anytime you have bipolar transistors, did you have transistors at all yet?
Yeah.
In what class?
Digital electronics.
Well, you had the, all right, well, for if you have any type of bipolar, not FET, but bipolar, you have to have a DC bias current to offset the actual quiescent point, right? Now, for FETs, you don't need that because it's basically a capacitor. It's the gate, right, that prevents it. Okay. Anyway, back to this thing. I've got to draw my little Smith chart here. So here we go with the Smith. You know that Smith chart out there in the hall? I wish that thing was portable. Because that's a big one, you know? That's perfect for this.
That's huge.
All right, here's, I know it is. So what's the first step always, guys?
Normalize.
Yeah, ZL. What's it going to be?
0.2 minus,
Let me just write this down. This is for people watching on the internet. Yes. Oh, and it's over 50. Right? So that's 0.2 minus J 0.7. Isn't it, class?
yeah.
All right, let's locate that point. We've got 0.2. Now that's a circle. Take a look. That's way out here, isn't it? Look at that trajectory, 0.2 for the real part. And then minus J 0.7 is down. This is minus J1, so it's about here. So if you look at this trajectory, your first point should be about here, and it's going to be 0.2 minus J 0.7. Can you all see that on your, take a look on your Smith charts?
Yeah, it's about there.
Find it. Make sure you can. Chase, can you see this?
Yes, sir.
All right. You good with this? Now the next thing you have to do, well, you can do this in any order you want, but I shoot a line right through there, out to the edge, and give me the wavelengths towards generator.
0.400.
Remember, you got to go right through there and through here and where this hits. 0.400?
I think so.
400?
Yeah.
I got about that.
Okay, good. Land it. All right, now, next take your compass. Some people are ahead of me. And just draw a circle of this radius here. So you're going to take that. You're going to draw something like this. Y'all with me? Hope yours works, Chase. You look like you're fighting with it.
Yeah, I lost the pencil that one. It's all right.
I have, my father was a draftsman, among other things, and he gave me a set of his drawing tools, and they're really nice. I mean, I've got stuff there I've never used for all sorts of things. Okay. So, now, where do you think I'm going to go? What are my options? I'm going to move around this circle. If I'm matching, I'm going to hit 2 points. That's the first point, right? And I can hit here, right? Now hear me. When I hit this point, we'll move it. Just draw a line right through there. And give me the value of wavelengths towards generator here. It's going to be, and you can give me the actual value. It's 1 plus J something. I don't know what J something is.
1 plus J 2.4 and wavelength is 0.1.
2.4?
Yes, sir.
And the conjugate would be 1 minus J 2.4, right? All right, for this one, what did you get wavelengths towards generator?
0.194.
194. All right. Y'all with me? So, when you get that drawn, I want you to hear me now. This is the rationale. So, I know we're putting a capacitor in series with it, correct? A capacitor has a minus J over omega C reactance. You all with me, class? So we want, if we're going to use that to nullify something, it has to be a positive J something. You see how that's positive J something? That's where we stop if we're putting a capacitor in series. Agreed, class? Y'all follow the rationale behind it. All right. So this has a real part of J 1.4. We have to add a reactive part right here. It would be normalized. Its normalized value right here would be minus J 2.4. Right? That would be the normalized value, correct, class? You all follow me? All right, so I'm going to come over here and I'm going to say, this is, normally this, I label these things on tests and stuff. I like 1, this is 2, second point. So now I come over here and I say, well, minus J 2.4 is the normalized value of the capacitive reactance. Capacitive reactance is minus J over omega C. And if it's normalized, it's divided by Z naught. Everybody follow me? Normalization, that was the normalized value. I could multiply that by Z naught, but I chose to do it this way. Can you all see this? Do you need another tool to write with? Okay.
Make it work.
I got a pen if you want. I mean, this is, it's not my pen, it's laying here. I don't need a key.
No, I care about it.
Do you need a pencil?
Yeah, I'll take a pencil.
All right, so what happens? You see the minus J's cancel? What do I have? I have C equals 1 over, and this is going to be 2.4 omega Z naught. So what's that value going to be? It's 1 over 2.4. Omega is 2 pi, right, times 10 to the 9th. And then Z naught for this one was 50, right? Can you tell me what that is? Hopefully it's right.
I got 1.33 picofarad.
1.33 picofarads. Anybody confirm or deny that? I get weird numbers on quizzes. I'll tell you one thing I've noticed about a lot of students are not used to being exact and getting partial credit. So I give no partial credit on this stuff. I mean, you got to be exact. You can't be sloppy. And I try to strive to do that because in the real world, sloppiness like that costs a lot of money. Do you know about what happened to the stuff they sent to Mars? It was the Mars rover and stuff. They lost, I don't know how many billions of dollars in this because somebody got sloppy and didn't check the units. Basically, inches and meters they messed up. And I'm not kidding about this. And there goes, I don't know how many billions of dollars down the tube. I mean, this is like, you do that in a private industry, this is the government underwrote. You're going to be out the door in a heartbeat. They have zero tolerance for losing massive amounts of money. And something like that should have been double checked, triple checked, and everything like that. Do you know what happened with the Challenger disaster? You know the space shuttle that blew up before you were born?
Yeah.
You know why it blew up? Because they used an O-ring. What?
I thought it was too cold that day and it wasn't flexible.
Nothing like that. All right, they used an O-ring for liquid oxygen. They had an O-ring that is rated at temperatures much, much higher than that. So when you have a liquid fuel, that basically was this, they didn't even test this thing, which is crazy. A guy named Richard Feynman, a Nobel Prize winner in physics, was before Congress, and he just used liquid nitrogen. He said, you used liquid fuel. And the reason that thing failed was because you guys didn't do your due diligence. Everything's supposed to be tested, every phase of it. They didn't test it. It was Morton thiokol. So he took the O-ring, and he had liquid nitrogen. They say liquid oxygen. Liquid nitrogen isn't that clear. Stuck it in there, took it out, and dropped it on the desk, cracked it into a million pieces. What happened, an O-ring is a seal, right? What happened is, when that rocket's taken off, the O-ring just fractured into a billion particles, and all this liquid oxygen turned into oxygen, which is an extreme accelerant, and the burn just blew the rocket, came up there, and it blew the rocket into bits and killed a bunch of people, killed the astronauts. So there's high schools up in Huntsville called Challenger and stuff like this, in memory of them. That kind of mistake is intolerable. All right, it caused the death. Nobody got their head knocked off in terms of death. But in the real world, in the old days at least, if you built a building and collapsed on somebody, I think the Romans started this. Basically, the people that engineered that off with their heads, or they hung them or something. Anyway, in a real world, if you do that kind of stuff, you get fired in a heartbeat. You may never work again. Just remember this. Double check, triple check things and be very precise. Okay, do y'all follow me on this one? That was my little story about some of the reasons for being exact. It's not because the professors or anybody was trying to be hard about it, but if you don't develop these habits and you get sloppy, hope for partial credit. In the real world, you get fired, you may go to jail.
You also had to find D. Is D just like it's 0.194
Yeah,
plus
I'm
0.5
sorry.
minus?
You're absolutely right. Let's find D. There's the mile marker we ended at, right? 0.194. Where did we start at? 0.400. That's negative, isn't it? I have to add 0.5. What do you get in terms of wavelengths towards each other?
I got 0.294.
0.294, anybody? All right. 0.294 lambda. By the way, what is the wavelength if we assume we're propagating at the speed of light? What is lambda? Well, what is lambda in free space? Well, it's 2 pi over beta, one way to get it, right? Well, what's beta in free space if it's lossless? Isn't it omega times square root of mu epsilon? Isn't that omega over c? So what is this going to be? In free space, it's always going to be c over f. Right. Just think, the wavelength is always 1 meter at 300 megahertz because the speed of light is 3 times 10 to the 8. 300 megahertz is 3 times 10 to the 8. All right. As frequency goes up, the wavelength gets shorter. See, it's inversely proportional. So what's the wavelength at a gigahertz? 3 times 10 to the 8th over 10 to the 9th, or what? 30 centimeters. Do y'all follow me? How big is 30 centimeters? Is this about a meter? Roughly? It's about a third of that. That's about 30 centimeters. So let's figure out how big it is in terms of that. Let's put 0.294 of that. 0.2, just call it 0.3 of 30 centimeters, or a third of that roughly is what? About 10 centimeters?
Yeah.
What's 10 centimeters? Do y'all know if you got a feel for that? Something like that, right? About that. That's actually long. See, most of the time when we do matching on printed circuit boards and stuff, we're talking about dimensions. We don't want more than a couple centimeters at most. All right, so we use other methods of matching. You're going to see this as time goes by. Y'all hear me on this, guys? Okay. Got another one for me?
Those are the only two you assigned.
I mean, let's go one step further before I get into the impedance matching with using parallel or shunt elements. So what about this one? What if I wanted to match it here? How far would I go and what element would I use? Hint, it's an inductor.
Yeah.
Use an inductor and you go past it.
All right, so let's do it just to complete this thought. All right, so if we don't want a capacitor, we won't want an inductor, right? We're going to put an inductor here. We don't know what the value of that inductor is yet, but if the inductive react, well, we're going to figure this out in a second. So here's my load. I wish I knew what happened to my markers. And this is Z naught. And it's 50 ohms. And this was 10 minus J35. All right, so we were here. All right, now we have to go to this point. I'll call this point 3. So what's the wavelengths towards generator number there? This one you didn't.
I got 0.306.
Anybody confirm that? 0.306?
Just about that, yeah.
0.306 lambda. All right. That means this distance to the point where we attach this is going to be 0.306 minus, we start at 0.4, 0.400, and that's negative, so we have to add 0.5, and this is all in terms of lambda, and this is how far we go, which I'll just call this D2. What is that?
I got about 0.406.
Anybody confirm? 0.406? I think that's right. Okay. Now, the value here is 1 minus J 2.4, so this has to have a normalized impedance of J 2.4, correct? That's normalized. So, I mean, you can do it several ways, but start with the impedance of an inductor. That's J omega L. If we normalize it, we divide it by Z naught. You all with me? So divide it by Z naught. And that would be equal to J 2.4. Most of this you're going to see, and it'll be intuitive after a while, but until you do several of these problems, it's not that intuitive. You all with me? So come over here, I can find L is going to be 2.4, right, times Z naught over omega, or 2 pi times 10 to the 9. What's that going to be? Z naught is 50.
I got 19.1 nano.
Anybody confirm that? Sure. Anybody? You got that, Chase?
Yes, sir.
All right. You guys get it? I say this because sometimes the first answer isn't the right. You guys got that?
No, that's right.
Okay. So that's the two types of matching we can do with series elements, right? Now we're going to do the shunt elements. Did you have this before with me or not? Shunt.
Yes, sir.
Okay. Shunt element is probably more common, but almost always it's a capacitor. But I can't speak from a whole lot of experience with this. And the stuff I've worked with, we usually use, we're going to do stuff when we have transmission lines. We actually use the transmission lines shorted and open as stub tuners. But right now we're going to do solid elements. So you'll see the rest later, shortly. I don't know in his book if he breaks it down quite like this, but just call this shunt matching. That was series, this is shunt matching. Okay. Now, here's what happens. Some of these are a little better. Yeah, this one's going to work. So when we talk about shunt, it's the same thing as in parallel. So over here we have an impedance, ZL, and we have a characteristic impedance of the transmission line, Z naught. But here we're going to put something in parallel. All right, we're going to put something here in parallel. That's the idea. It'll be located at some distance D, and this will have some, now think about this, if you have impedance, 1 over impedance is conductance, it will have a reactive portion of conductance. All right, now just listen to me and so you can follow this. Here is a Smith chart, my Smith chart. Here's the one circle. Here's how we do it. I just want you to be attentive. And this is with elements. So the first thing is we're going to find ZL, which is capital ZL over small or over Z naught. I think you got that down. Everybody with me? I'm going to just pick a point. So I'm going to pick this point. Say it's 0.5 and J 0.1. I'm just going to do this because I need something to work with. So it's going to be 1/2 plus J1. So where's J1? Here's J1, right? And this would be the trajectory. And the 1/2 would be something like this. So here's my first point, right? It's ZL, and I just put it as 1/2 minus J, or plus J1, or J1. Y'all follow me on that? All right, now, take your straight edge and draw a line right from the center, right through here, like so. Just right through the whole thing, go through the bottom too, right through the whole Smith chart, top through bottom. Has to be from the point where ZL is to Z naught. Everybody with me? Go ahead and do it. I want you to see this clearly. The reason you're going to see this, because we're going to very easily get the value of the admittance, which is 1 over ZL, the normalized admittance. Now, this is ZL. When you take your compass now and draw a circle of this radius, constant reflection coefficient, and you draw a circle that big, something like this. This is a constant reflection coefficient. You're going to come to a point that's the conjugate point. It's exactly through the center here where this straight line intercepts your radius circle, and this is YL. It's the normalized load admittance, which is 1 over ZL. You all follow me in this class? Now we're in the admittance domain. You all know what admittances are, right? Like if you have resistance of 10 ohms, the admittance of that would be 1 over 10 or be 0.1, and it's Siemens, right? Correct, class? You all with me? I mean, we don't use that very much, but you need to be at least appreciate what I'm doing here. This is admittance, right? Now, there's going to be a point here where you read something wavelengths towards generator. Can you just tell me about what that is? Eyeball it.
I got 0.386.
Anybody else?
Yeah, I agree about that.
0.386 lambda. That's the starting point. We're going to move from there, and I want you to hear me now. Just like we did before, but remember, we are in the admittance domain. Got me? And we're going to move from there until we hit here, the 1 circle. So we're going to move all the way around. That was our normalized load admittance until I hit here. And then draw a line right through there, as we've done before. And give me the wavelengths towards generator. And remember, this point is going to be, and I'll call this, that was 0.1, this is 0.2. Call this 0.3. And this is going to be 1 plus J something. Go ahead.
Oh, you want the J value? It's going to be J 1.6.
All right. Now, while I'm at it, and you guys are giving me that, shoot a line right through here where it intersects here. That's 0.3, this is 0.4. And shoot a line through there. And then give me the wavelengths towards generator here. We should have brought some water down here first.
What did you want from that? You wanted wavelengths or generator?
Yeah.
I got.
Is this the one you got or the other one?
Oh, I can do either.
Give them both.
Both. The top one's going to be 1.78 lambda.
No, 0.178.
Oh, 0.178. Yeah.
0.178 lambda.
Yeah,
And bottom one? 0.2 what?
lambda. This one's going to be wavelengths or generator. That's the outside. So it's going to be 0.321, I guess.
Okay, 0.32 what?
0.325, I guess. 0.321.
Anybody confirm those?
It's around there, yeah.
I'm going to tell you, you're going to get a little slop, all right? But it's about that. Got me, everyone?
I think it's 0.321.
All right, now we're going to parse this, all right? Now, if we land on this point, we have a normalized input admittance of 1 plus J6. And here's what I'm going to do. I tell you, I missed the day of erasers. This thing's seen better days. So I'm going to just show you this. Remember, I'm going to move, and when I move to a distance of, well, we didn't calculate this distance. If we move to this point right here, this distance is going to be 0.178, right? That's where we ended up, minus 0.386, right? Minus 0.386, but we have to add 0.5. So what is that in terms of wavelengths?
Get it real quick. I got 0.292.
Anybody else? I think you're right.
It's 0.178 minus 0.386. Oh, yeah. Yeah, 0.292.
0.292 lambda. With me on this, class? So I move there, and I see my normalized admittance is 1 plus J 1.6. So I need to add a minus J 1.6 admittance. Do y'all hear me? So I want to add to this, and this is in the Y domain, remember, a minus J 1.6 if I go that far. So now, oh, in parallel, pardon, in parallel. This is shunts. In parallel. Has to be in parallel. That's how you add admittances. You add them in parallel. So this is going to be minus J 1.6 at this distance. So think about this. This is an admittance. If we have an inductor L or capacitor C, I want you to just follow this. If we talk about the impedance of these, the inductor is J omega L. The capacitor is 1 over J omega C, or minus J over omega C, the impedances of either. If we talk about the admittances, Y, for an inductor, it's 1 over J omega L, and for a capacitor, the admittance is J omega C. Can you all follow me on the rational? Now, if you want the normalized admittance, if you start here with impedance, we can get normalized impedance of an inductor by Z naught. Take 1 over that, minus J Z naught would be the normalized admittance. Y'all follow me in this class? This would be normalized impedance, that would be normalized admittance. Y'all follow me?
So it should be Y in terms of Y?
Y is admittance. It's a symbol for admittance.
Yes, but should Z not be in terms of Y, or is it still, that's still in terms of Z naught?
Well, here's the deal. We could normalize it in terms of Y naught, but here, if you just take this and flip it, it becomes
Oh,
Y.
okay.
So this, I leave it this way, it's minus J Z naught over omega L. It's still an admittance normalized, it's just flipping the normalized impedance. Over here, this becomes what? Times Z naught. Everybody with me? Now, it's in parallel. Admittances are always in parallel. That's how you add it. Y'all with me, class? So, I have to put that on parallel. I need a value that's got a minus J 1.6 normalized value. That's going to be an inductor, isn't it, class? So I say, this is it right here. I come over here and I say minus J 1.6, that's the normalized impedance I need, is equal to minus J, and this is going to be Z naught, whatever that is, over omega L. And you can calculate L from there. Obviously, you can see L is going to be equal to Z naught over omega times 1.6. Y'all with me? That's in parallel. That's a bad design. It shorts out DC. I'm just telling you that. It's a very bad design. But I'm just showing you if it was, that's what it would be. Now, I didn't give you omega. I'll give you F as 10 to the 9th hertz, a megahertz. And I'll give you Z naught is, say, 50. And I already normalized that, right? I gave you ZL as 1/2 plus J1, so that's really 25 plus J50 is ZL. Right, is ZL in terms of impedance, just multiply the normalized value by Z naught. Correct, class? So now we're going to get the value of L here. It would be in parallel. What would it be?
I got 4.97 nanohenries.
All right,
Yeah.
so it's 50 over 2 pi, 10 to the 9th, and then 1.6 according to what we have. Do you all agree with that? What did you get?
4.97 nanohenries. We got the same thing.
Yeah.
4.97 nanoamp. Bad design. An inductor in parallel shorts out DC. Just level them. If you have a choice, don't do it. You don't want that. I got other stories about it, but you really don't want that. I'll tell you why. If there is any DC on that line, that inductor will probably burn out because it'll act like a short and it acts like a fuse. Inductors will pop in a second unless they're really thick wire. So next, we're going to keep going. We're going to go to the next point. You all hear me? So that's the inductor. Now I want to go to this point. but I want to do it with the capacity. So I'm going to erase this. And remember, they're in parallel. Shunt matching. So here I have my ZL. I have my Z naught of 50. I have this is, what is that? 25 plus J50, so the normalized is the same thing. And now I have to go a little further, and I have to put a parallel. This is going to be a capacitor. This is a good design. So you come out here, remember it's in shunt. Everybody with me? So we're in the admittance domain. I'm going to move to here, right? I'm going to move to 0.4. So the total distance I move is going to be what? Where did I land? 0.325, is that right,
Yeah.
class? So this is 0.325 minus
0.386.
0.386. Got to add 0.5 to it because it'll be negative lambda. What's that?
0.439.
That's a long way. Okay? So that's how far I move. Now, when I hit that point, I get a value here of 1 minus J1.6. Do y'all agree with that? Remember, it's admittance. It's normalized admittance. Correct, class? I need something with a plus J1.6 to get rid of it. So that means this value, the normalized admittance of this has to be plus J1.6. And you can see why I did that. You come over here, here's the normalized admittance for a capacitor, right? You all with me? So I just set J1.6 equal to J, and this, it's going to be omega C Z naught. Omega C Z naught. That means that C itself is 1.6, right? And now it's divided by omega, which is 2 pi times 10 to the 9th, Z naught, and I made Z naught 50. What's that value going to be?
5.09 picofarad.
5.09? Is that right, class?
Yeah.
That's not too bad. When you get sub-picofarad values, you're really dealing with stuff where just the length of wire, if you don't have real short leads, will affect it significantly. When I teach EMC, I teach a lot of stuff about compatibility and FCC regs and CISPRI and all this other stuff and how to meet regulations. One of the worst things to do is talk about like 0.45 picofarads. What you have to do is get a picofarad capacitor in that ballpark, and then you have to put what's called a variable capacitor near it in parallel with it that you can adjust to tweak it down to the actual value. Just because the leads themselves, do you all know this? Have you been told this? That cut the lead lengths as short as possible because the amount of inductance in a lead that long, or I should say, the effect on total inductance, both external and internal inductance on a lead that long at a couple of gigahertz is maybe larger than the inductor that you actually need for the matching. You got to be aware of that. Same with capacitor. There's all sorts of stray capacitance between leads and inductance. Just be aware of that for now. At high frequencies, it's a nightmare. And when high frequencies, I mean a gigahertz and on up. It just goes bananas doing engineering. You have to use dielectric screwdrivers to tune things and all that. If you get near it, it'll change the resonant frequency. Okay. So those are the two ways to match in shunt using elements. And I showed you the two ways of matching in series using impedances, right? We're always using either inductors or capacitors because they draw no power for matching. Y'all with me? Now what we're going to do is actually use a transmission line to replace the inductors and capacitors. And we're going to do it, first we'll start with the series matching, even though I could do it in parallel right now too. I'm going to show you this. This is not the most common way it's done, by the way. but I guess it is done often enough that Whitmer's book talks about it, and frankly, it's worth knowing how to do this. I just realized that. What time do you have?
2:13.
I may do this next time, but to be frank about it, I just want to give you a heads up on one thing. If you think, remember, if you want to get an impedance, remember, we just care about impedances that are plus or minus J something. Y'all with me? So just follow me on this. If you have a standard transmission line, a characteristic impedance Z naught, and I put a short circuit on it for a load, what is ZL for a short circuit?
Zero.
Zero. What's the normalized value? Zero. People stop. It's a trick question. Notice, just zero divided by anything, still zero if the anything's got any value. All right, other than zero. All right, so where's that point on this Smith chart? Right here.
Yeah.
That's zero. Take a look. Just convince yourself. This point is what? Infinity, right. So if that's zero, that's where you start. Now, as I move from there, just think, you'd have to draw a radius this big, have a reflection coefficient of 1, that it would. A short circuit has a reflection coefficient in magnitude of 1. And you'd move this way. If you want a normalized impedance, remember, we're using the transmission line. Say we've got a plus or a minus J something. Minus J1, we want to get rid of it. We move from here to here. Here's plus J1. It's exactly 1/4 of that circle, or lambda over 8. Do you all follow me? Take that and stick it in series. Do you all follow me? Can you all understand that? I'm replacing that element that was an inductor with a transmission line in series. You'll see this. If we wanted an admittance, and if you think about this, if the impedance is 0, what is the normalized admittance? What's 1 over 0? Big number, right? Infinite, right? Then if you want the admittance, you come over here and start this mess. I'll take you through it next time. I know I owe you a quiz, so you're about to get it. Would you do me a favor? I like to give people every other row, so can you two move over there? You stay put. You guys move here, and you can move over there. Or you guys can move over to the far right. And I appreciate your time. I'm sorry I didn't cover more today, but I really tried. Does anybody need a Smith chart? All right, we seem to have an abundance.
We have a bunch.
Yeah, there's